Today's topic is flip-flops. Gates are decision-making elements. They can perform binary addition and subtraction. Flip-flops are memory elements. The devices that can store a binary digit. A flip-flop is a device with two stable states. It remains in one of these states until triggered into the other. RS latch. RS latch is the simplest flip-flop with two stable states. It remains in one of these states until triggered into the other. RS latch using transistors is shown in this figure. It is transistor latch. Two transistor latch is shown in this figure. Collector of one transistor drives the base of other transistor through a 100 kilo ohm resistor. We see two transistors are used in this figure, and collector of a transistor is connected to the base of other transistor through 100 kilo ohm resistance. In a circuit like this, one of the transistors is saturated and the other is cut off. If we connect two transistors, such as collector of one transistor is connected to the base of other transistor through a resistance, then in such a circuit we see that one transistor will be in saturation condition, that is saturated, and the other transistor is in cut-off condition. A transistor is called saturated when emitter current flows through it. A saturation emitter current flows through it, and a transistor is called in cut-off state when no emitter current flows through it. We see in this figure the transistor in shaded form is in cut-off condition, and the unshaded transistor is in saturation condition. One of the transistor will be in saturation condition and the other will be in cut-off condition. In this figure, the transistor of left side is in cut-off state and the transistor on the right side is in saturation condition. In this figure, the situation is reversed. The transistor on the left is in saturation condition and transistor on the right is in cutoff condition. So one of the two transistors will be in saturation condition while the other will be in cutoff condition. If the right transistor is saturated, that is in figure A, that is in this figure, right side transistor is in saturation condition. If right side transistor is saturated, it means ammeter current flows through it. Then the potential at its collector will be almost zero. So the base potential of left transistor will becomes almost zero, which puts the left transistor into cutoff and no ammeter current flows through it. In this condition, the output obtained at the collector of right transistor, which we represent by Q, will be 0, that is low voltage, which represent 0 binary number. And if we see this figure, if left transistor is in saturation condition, left transistor is saturated, ammeter current flows through it. Similarly, if the left transistor is saturated, that is in figure B, the right transistor is cut off and Q is approximately plus 5 volt high. So if right transistor is saturated, output at its collector Q will be low, that is 0. And in this second case, when this right transistor is cuts off, it happened when left transistor is in saturation condition. Then in this situation, the output at collector of right transistor, that is Q, will be high, plus 5 volt. Output Q, which is obtained at the collector of right transistor, can be low or high, that is binary 0 or 1. If latched as shown in figure A, the circuit is storing a binary 0 because Q is 0, and if latched as shown in figure B, the circuit is storing a binary 1 because output Q is 1. In this figure A, this circuit store a binary 0 because Q is low, and in this circuit it will store a binary 1 because output Q is high. Output Q will be high when this right transistor will be in cutoff condition, and it will be low when this right transistor is in saturation condition. Control inputs. To control the bit stored in the latch, inputs S, which is called set input, and R, which is called reset input. These two control inputs are added as shown in the figure C. This is the figure C. Here two control inputs S and R are added as shown in this figure. S is known as set input and R is known as reset input. Set is for output Q equal to 1 and reset for output Q equal to 0. A high set input S forces the left transistor to saturate. If control input S is high, a high voltage is applied at the base of left transistor and it gets saturated. Ammeter current flows through it. If left transistor is saturated, this right transistor will be in cutoff and output Q will be 1. So this control input S, if it is high, then we get a high output Q. A high set input S forces the left transistor to saturate and right transistor cuts off, so overall circuit latches and output Q equal to 1. Once set, the output will remain a 1 even though the input S goes back to 0 volt. A high reset input R. If we put this control input R, that is reset input, equal to 1, high voltage is given at R, then this forces the right transistor to be saturated, and then output Q will be low, that is 0. So this R reset control, if it is high, the Q is 0, low, and the circuit resets. Resets means we get 0 output. Set by set we means we get high output. To set, we have to put S equal to 1, that is high, and for reset we have to put R equal to 1, R high. In figure C, Q represents the stored bit. A complementary output Q bar is available from the collector of the left transistor. This output Q we obtain here is at the collector of right transistor. If we want output at collector of left transistor, then it will be Q bar. It will be complement of Q. If Q is 0, if output of right transistor is 0, then output of left transistor at its collector will be 1. If output obtained at collector of right transistor is Q, output obtained at collector of left transistor will be Q bar. Truth table. This is the truth table. When R is 0, S is 0, output Q we write NC, means no change. If R is 0, S is 0, these are two control inputs. R for reset, S for set, and Q is output at the collector of right transistor, and if R is 0, S is 0, we have no change at output of right transistor. No change means if it is 0 initially, then it will be 0. If initially it is 1, then it will be 1. Now if R is 0 and S is 1, then output Q will be 1. And if R is 1 and S is 0, then output Q will be 0. And in last situation, when both the control inputs R and S are 1, then it will represent a race condition which we represent by star. Race condition. When both control inputs S and R are high simultaneously, this is called a race condition. It is never used because it leads to unpredictable operation. This condition we have to avoid it. If both control inputs are high, both transistors saturate. When these inputs return to low, both transistors try to come out of saturation. It is a race between two transistors to see which one will desaturate first. The faster transistor will win the race and latch the circuit. In mass production, either transistor can be faster, therefore the Q output is unpredictable. We cannot predict what will be the output. This condition is known as race condition. So this was RS latch using transistors. Nowadays we build RS latches with NOR gates and NAND gates instead of using transistors. This figure E shows how RS latch is formed by using NOR gates. This is RS latch using two NOR gates. Output of each NOR gate is connected to the input of other NOR gate, and there are two control inputs. One is R and other is S, connected as shown in this figure. Output obtained from one NOR gate is Q, while output obtained at other NOR gate will be Q bar. It is the complement of Q. This is its equivalent De Morgan equivalent circuit. This is RS latch using NOR gates, and in this circuit we use AND gates with inverted inputs. So this circuit is equivalent of this circuit according to De Morgan's theorem. So this is De Morgan equivalent of this circuit. This is the truth table for this RS latch. And this figure G shows timing diagrams. Look at the truth table. When both R and S are 0, then output Q is no change. And when R is 0, S is 1, output Q is 1, because set input S is high, so we get high output. And if R is 1 and S is 0, then output Q will be 0. Here reset input is high, so it will reset the output to 0. And at last, when R and S both are 1, then it represents a race condition which we should avoid. So we should avoid this condition that R is 1 and S is 1. In this diagram, these are the two waveforms for R and S, and the third one is for output Q. Initially, we have R high and S low, R1, S0. So output Q is 0 because it is reset. Now this output Q will become 1 when R become 0 and S is 0, then output will not be changed, and output Q will be changed only when S become 1 and R become 0, then it goes high, it sets, and it remains high even when this set signal goes low, and this output Q will goes low when R goes high. Then it resets. R goes high and S is low, then it resets and becomes 0. and it remains 0 even when R becomes 0. Then again output Q will become again high when S become high, and so on. In this way, this is the timing diagram according to this truth table for this circuit RS latch using NOR gates. Similarly, we can find Nand latches. This is the RS circuit using Nand latch. Here we use two NAND gates. Output of one is connected to the input of the other, and this is its equivalent De Morgan circuit. NAND gate is converted to OR gate and its inputs are inverted. The bubbles represent inverted inputs. So this is according to De Morgan theorem. So it is De Morgan's equivalent of this circuit. Now look at the truth table of this circuit. When R is 0, S is 0, now it represents this as race condition. In this circuit, race condition is for R 0, S 0. And when R is 1, S is 1, it is no change. So these two conditions are interchanged for RS latch using NOR gates and for RS latch using NAND gates. Race condition is for different inputs. If we use NOR gates, then race condition is for R equal to 1, S equal to 1. And now if we use NAND gates, then race condition is for R equal to 0, S equal to 0. And this race condition we have to avoid. So initially in timing diagram, we can put R equal to 1, S equal to 1 or R1, S0 or R0, S1. We do not take initially R is 0 and S is 0 for this NAND latch, and similarly for this NOR latch, here the race condition is for R1, S1, so we have to avoid this. Initially we should not keep R1 and S1. Switch debouncers. RS latches are often used as switch debouncers. Whenever we throw a switch from the open to the closed position, the contacts bounce and the switch alternately makes and break. For a few milliseconds before finally setting in the closed position. To eliminate the effects of contact bounces, RS latch is used with the switch as shown in above figure. So RS latch is connected with this switch as shown in this figure, and in this way it is used as switch debouncers. This is the switch which is connected to start and clear. These are 6 points. 2, 1 and 2 are inputs of upper inverted OR gate, and 4 and 5 are 2 inputs for lower inverted OR gate, and 3 and 6 are outputs of these gates. One is CLR bar and one is CLR. CLR is for clear. Clear means 0, and CLR bar is its complement of CLR. In this figure we see if pin 1 is low and pin 5 is high. Pin 1 is low because pin 1 is connected to ground, and pin 5 is open. So this open will behave as high input. So in this diagram we initially put here pin 1 as low and pin 5 as high. If now this switch is connected to clear, then pin 5 will become 0, and due to contact bounces this will changes from 0 to 1 and 1 to 0 for small time intervals several times. And similarly, if this key is then connected to start, it will again, the pin 1 will begin to change for few milliseconds several times between 1 and 0 states. But if we use this RS latch, then we see that this effect of contact bounce will be disappeared, because in RS latch we see that if R is 0, S is 1, Q is 1. If S set input is 1, output Q is 1. And then if set comes to 0, then output will not come to 0, it will remains 1. It will go to 0 only when R becomes 1. This property is used here, and if the switch which bounces after few milliseconds intervals several times, this effect will be disappeared using this RS latch, and this application is known as switch debouncers. Level clocking. Computers use thousands of flip-flops to coordinate the overall action. A square wave signal called the clock is sent to each flip-flop. This square wave signal is shown in this figure. We write it by CLK. CLK means clock, and clock is nothing but an square wave signal. it will become 1, then it becomes 0, then become 1, then become 0 after a fixed time interval. So this is a clock signal. This clock signal is sent to each flip-flop This is to coordinate the overall action. A square wave signal called the clock is sent to each flip-flop. This signal prevents the flip-flops from changing states until the right time. If we use this clock signal, it will prevent the flip-flops from changing states until the right time. This is clocked latch. S and R are two inputs. S is for set and R is for reset. And now a clock signal, that is a square wave signal, is applied. Each of the one of the inputs of two NAND gates. And then we use two inverted OR gates connected as shown in this figure, and outputs are obtained as Q and Q bar. This is its equivalent circuit. Two bubbles are cancelled out. This is the truth table for this circuit. Now with two control inputs R and S, we have this clock signal also. If clock is 0, then the truth table shows that if R and S changes, there will be no change in output Q. And when clock is 1, output Q will be obtained as in previous tables of RS latch. That is, if clock is 1, then high S and low R will give 1, and high R and low S will give 0. High R means it resets and output Q will be 0, and high S means it will set and output Q will be 1. And R equal to 1 and S equal to 1 with this clock equal to 1 now gives the race condition. So the output signal will change only when the clock goes to high. This is shown in this timing diagram. Initially R is low and S is low. Output Q is low. Output Q we can assume as low or high. If we assume it as low, when R is low and S is low, and we assume that output Q is low. Then when S becomes high, then this output Q will not become high. It goes to high only when next positive clock edge comes. In figure A pair of NAND gates drive a NAND latch. S and R signals drive the input gates. The inner control signals are labeled as R dash and S dash. A low R dash and a high S dash set Q to 1, while a low S dash and a high R dash reset Q to 0. R dash and S dash are normally high when the latch is inactive. As a double inversion cancels out, figure B shows circuit that is equivalent to that of figure A. We see that a high S and high clock force Q to go high. So if we use this clock signal, then when S goes to high, output Q will not go to high until this clock goes to high. Positive and negative clocking. Clock is a square wave signal. A low clock prevents S and R from controlling the latch. If a high S and low R drive the gate inputs, the latch must wait until the clock goes high before Q can be set to 1. Similarly, given a low S and high R, the latch must wait until the clock goes high before Q can be set to 0. This is positive clocking, in which latch wait until the clock signal is high before the output can change. This type of clocking is known as positive clocking. Otherwise, if we take its opposite, that is negative clocking. In negative clocking, an inverter is added between clock and the input gates. In this case, the latch wait until the clock signal is low before the output can change. Positive and negative clocking are often called level clocking because the flip-flop responds to the level, high or low, of clock signal. It is the simplest way to control the flip-flops with a clock. High clock, high R and high S is the race condition which should be avoided.